Tonight, we're going to explore one of the most violent things that can happen at the smallest scale in nature. There is a particle out there, a real particle, that is identical to the electron in almost every way. Same mass, same spin. But the moment it touches ordinary matter, something catastrophic happens. It doesn't bounce off. It doesn't get absorbed. It and the electron it meets are both completely erased from existence, converted entirely into pure energy. No debris, no remnants, just a flash of radiation and then nothing. This particle is called the positron, and the reason it cannot survive in our universe, the reason matter destroys it almost instantly, is one of the most profound and unsettling truths in all of physics. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know, even if you don't think about it very often. Everything around you is made of atoms. The chair you're sitting in, the air filling your lungs, the screen in front of you, your own body. All of it, every last bit, is constructed from atoms, and every single one of those atoms contains electrons. Tiny, almost unimaginably small particles carrying a negative electrical charge, orbiting the nucleus at the center of each atom. Electrons are everywhere. They are in every molecule of nitrogen and oxygen in the atmosphere. They are in the water you drink, the food you eat, the ground beneath your feet. There are roughly 10 to the 28th power electrons in your body alone. That is a 1 followed by 28 zeros. A number so large it is essentially meaningless to the human mind. But the point is simple. Electrons are not rare or exotic. They are the most common charged particle in the ordinary matter that fills our world. You cannot escape them. You are surrounded on all sides, at all times, by an ocean of electrons. Every surface you could ever touch, every gas you could ever breathe, every liquid you could ever swim through is saturated with them. And this fact, this simple, obvious, unremarkable fact about our world, is what makes the existence of the positron so extraordinary and so doomed. Because the positron is the electron's perfect opposite. And in a universe made of matter, being the opposite of an electron is a death sentence. Let me explain what I mean by perfect opposite, because this is not a loose metaphor. The positron has exactly the same mass as the electron, not approximately the same, not close enough for practical purposes. Exactly the same. The electron has a mass of about 9.109 times 10 to the minus 31 kilograms. The positron has a mass of about 9.109 times 10 to the minus 31 kilograms. Identical. The positron also has the same spin as the electron. Spin is a quantum mechanical property that doesn't have a perfect everyday analogy, but you can think of it as a kind of intrinsic angular momentum that every fundamental particle possesses. The electron has a spin of 1/2. The positron has a spin of 1/2. Identical again. The positron even interacts with the same fundamental forces as the electron. It responds to the electromagnetic force. It responds to the weak nuclear force. In almost every measurable way, the positron is indistinguishable from the electron, except for one thing: its charge. The electron carries 1 unit of negative electrical charge. The positron carries 1 unit of positive electrical charge. That is the difference. That is the only fundamental difference between these two particles. One is negative, the other is positive. Mirror images. And this single difference is what makes their encounter so catastrophic. because opposite charges attract. And when a positron and an electron are drawn together by that attraction, what happens next is not a gentle meeting. It is annihilation. Both particles are completely destroyed. Their combined mass converted into energy in the form of gamma-ray photons. Nothing remains of either particle. They simply cease to exist. But we're getting ahead of ourselves. Before we talk about what happens when a positron meets an electron, we need to understand where the positron came from. Not physically, but conceptually. How did we even know this particle existed? Because for most of human history, nobody had any reason to suspect that such a thing was possible. The idea that every particle of matter might have a mirror twin, an opposite, a counterpart made of something called antimatter, that idea didn't come from experiment. It came from an equation. In 1928, a British physicist named Paul Dirac was working on one of the hardest problems in theoretical physics. He was trying to write an equation that described how electrons behave. Now, physicists already had equations for electrons. Schrödinger's equation, developed a few years earlier, did a reasonable job of describing how electrons move and interact at the quantum level. But Schrödinger's equation had a problem. It didn't account for special relativity. It described electrons as if they were slow-moving particles in a non-relativistic world. But Dirac wanted more. He wanted an equation that was fully consistent with both quantum mechanics and Einstein's theory of special relativity. He wanted to describe the electron as it truly is, a relativistic quantum particle. And so he sat down and worked out the mathematics. What emerged was the Dirac equation. And it was beautiful. It correctly described the electron's spin, which Schrödinger's equation could not. It correctly predicted the electron's magnetic moment, a quantity that measures how the electron interacts with magnetic fields. It was consistent with special relativity. It was elegant, precise, and powerful. But it also had a problem, a very strange problem. The Dirac equation had two sets of solutions. One set described particles with a negative charge and positive energy. These were electrons. That was expected. But the other set of solutions described particles with positive charge and negative energy. And that was not expected at all. At first, Dirac didn't know what to make of these extra solutions. Negative energy didn't make physical sense in any obvious way. Dirac tried various interpretations. He initially proposed something called the Dirac sea, an idea where all the negative energy states were already filled with electrons, and a hole in this sea would appear as a particle with positive charge. He first suggested these holes might be protons, since protons have positive charge. But that didn't work. Protons are nearly 2,000 times heavier than electrons, and the equation demanded that the mirror particle have exactly the same mass as the electron. Something else was going on. By 1931, Dirac made a bold prediction. He proposed that the mirror solutions described a completely new particle, a particle with the same mass as the electron, but with positive charge. A particle that no one had ever seen before. An anti-electron. He was predicting the existence of antimatter. This was an extraordinary moment in the history of physics. A theorist, working with nothing but mathematics, was claiming that nature must contain a particle that had never been observed. Not because of any experimental evidence, but because the mathematics demanded it. The equation wouldn't work without it. And if the mathematics was right, then somewhere out there, this particle was real. The scientific community was skeptical, and rightly so. Predictions from pure theory are only as good as the experiments that test them. But the wait was short. Astonishingly short. In 1932, less than a year after Dirac published his prediction, an American physicist named Carl Anderson was working at Caltech with a device called a cloud chamber. A cloud chamber is a sealed container filled with supersaturated vapor. When a charged particle passes through this vapor, it leaves a visible trail of tiny droplets, like a miniature contrail from a jet airplane. By placing the cloud chamber in a strong magnetic field, Anderson could study these trails. Charged particles curve in a magnetic field. Positive charges curve one way, negative charges curve the other, and the tighter the curve, the less momentum the particle has. By photographing these trails, Anderson could determine both the charge and the momentum of whatever particle had passed through. Anderson was studying cosmic rays, high-energy particles that constantly bombard Earth from space. Most of the trails he saw were from familiar particles. Electrons curving one way, protons curving the other. But one day, he saw something he couldn't explain. A trail that curved in the direction a positively charged particle would curve, but the curvature was too tight for it to be a proton. A proton, with its much larger mass, would leave a trail with a much wider curve at the same speed. This particle had the curvature of something with the mass of an electron, but it was curving the wrong way. It was curving as if it had a positive charge. Anderson checked his equipment. He checked the magnetic field orientation. He checked everything. The result held. He was looking at a particle with the mass of an electron and a positive charge. He had found Dirac's anti-electron. He had found the positron. But the story of how Anderson confirmed his discovery deserves a closer look, because it reveals something important about how science actually works. Anderson's first photographs of the strange trail were suggestive but not conclusive. A trail curving the wrong way could have alternative explanations. Maybe it was an electron moving in the opposite direction. Maybe the magnetic field had fluctuated. To rule out these possibilities, Anderson did something clever. He placed a lead plate across the middle of the cloud chamber. This plate was thick enough to slow any particle passing through it. If a particle entered from the top and hit the lead plate, it would lose energy and emerge from the other side, moving more slowly. A slower particle curves more tightly in a magnetic field, so Anderson could determine which direction the particle was moving by looking at which side of the lead plate showed the tighter curve. The photographs were unambiguous. The particle entered from below, hit the lead plate, lost energy, and curved more tightly above the plate. It was moving upward, and it was curving in the direction that only a positively charged particle would curve. It could not be an electron moving downward because the curvature was tighter on the wrong side of the plate. It could not be a proton because the curvature was far too tight for a particle with the mass of a proton. There was only one possibility: a particle with the mass of an electron and a positive charge. Exactly what Dirac had predicted. This lead plate was a stroke of experimental genius. Without it, Anderson would have had an interesting but ambiguous photograph. With it, he had proof. The lesson here is that great experimental physics is not just about having the right equipment. It is about designing the right test, asking nature a question in a way that forces a clear answer. Anderson asked the right question, and nature answered, positron. The discovery was confirmed by other experimenters shortly after. Anderson published his results, and the physics world took notice. Here was experimental proof that antimatter existed. Not as a theoretical concept, not as a mathematical trick, but as a real physical particle that could be detected, measured, and studied. Anderson received the Nobel Prize in Physics in 1936 for this discovery. He was only 31 years old. It is worth pausing here to appreciate just how remarkable this sequence of events was. A theorist writes an equation. The equation demands the existence of a particle that no one has ever seen. And within months, an experimenter on the other side of the world finds exactly that particle using completely independent methods. The universe, it turned out, was exactly as strange as the equation suggested. Now let's talk about what the positron actually is in physical terms, because understanding this clearly is essential to understanding why matter destroys it. The positron is the antiparticle of the electron. That is its formal designation. Every particle of matter in the standard model of particle physics has a corresponding antiparticle. The proton has the antiproton. The neutron has the antineutron. The neutrino has the antineutrino. And the electron has the positron. This is not optional. It is a requirement of the mathematics that describes how particles behave. Every particle must have an antiparticle. This requirement comes from a deep result in theoretical physics called the CPT theorem. CPT stands for charge conjugation, parity, and time reversal. The theorem states that if you take any physical process, replace every particle with its antiparticle, reflect everything in a mirror, and run the process backward in time, the result must be a valid physical process that obeys all the same laws. This is not something physicists chose or assumed. It is a mathematical consequence of the basic principles that underlie quantum field theory and special relativity. Any theory that is consistent with these principles must have CPT symmetry, and CPT symmetry requires that every particle has an antiparticle with the same mass, the same spin, and exactly opposite charge in other quantum numbers. This means that the existence of antimatter is not an accident. It is not a quirk of nature that could have been otherwise. It is a mathematical necessity built into the deepest structure of physics. As long as quantum mechanics and special relativity are correct, and they have been confirmed by every experiment ever performed, then antiparticles must exist. The positron is not optional, it is mandatory. The universe has no choice but to include it. Now, for some particles, the antiparticle is the same as the particle itself. The photon, for example, is its own antiparticle, but for the electron, the antiparticle is a distinct, separate particle with opposite charge. That particle is the positron. Here is what is critical to understand. The positron is not unstable in the way that some other particles are unstable. A free neutron, for example, is unstable. If you take a neutron and isolate it in empty space, far from any other matter, it will decay on its own in about 14 minutes on average. It falls apart into a proton, an electron, and an antineutrino. The neutron is inherently unstable, it cannot last. The positron is different. A positron sitting alone in completely empty space, far from any electrons, far from any matter of any kind, would last forever. It would never decay. It would never fall apart. There is no internal clock ticking down to its destruction. The positron on its own is a perfectly healthy, perfectly permanent particle. This is what makes the situation so striking. The positron's problem is not that it is flawed. The positron is a perfectly valid, perfectly stable particle. Its problem is its environment. The positron's problem is that it lives in a universe made almost entirely of matter. And matter is full of electrons. And electrons are the one thing a positron cannot survive encountering. This point deserves emphasis because it reveals something profound about the nature of the positron's predicament. There is nothing inherently wrong with antimatter. A universe made entirely of antimatter would function exactly like ours. Anti-hydrogen atoms would form, with antiprotons at their centers, and positrons orbiting around them, held together by exactly the same electromagnetic force that holds our hydrogen atoms together. Anti-hydrogen would have the same spectrum of light, the same chemical properties, the same ability to form molecules as ordinary hydrogen. Anti-stars could burn anti-hydrogen into anti-helium through the same nuclear fusion processes that power our sun. Anti-planets could form from the debris of anti-supernovae. Anti-water could flow in anti-rivers under anti-skies. If chemistry and biology work the same way with antimatter as they do with matter, and as far as we know they do, then anti-life could theoretically arise on an anti-planet, and anti-beings could look up at anti-stars and wonder about the universe, never knowing they were made of what we call antimatter. Because from their perspective, they would be made of matter. We would be the antimatter. This is not science fiction, it is a direct consequence of the CPT theorem and the symmetry properties of the laws of physics. An antimatter universe would be indistinguishable from a matter universe to anyone living inside it. The only difference would become apparent if matter from one universe somehow encountered antimatter from the other. Then annihilation would occur. Not because one type of matter is right and the other is wrong. Not because one is real and the other is fake, but simply because they are opposites, and the conservation laws permit their mutual conversion into energy. The positron is doomed not because it is defective, but because it is outnumbered. In a universe where matter and antimatter existed in equal quantities, positrons and electrons would be equally common and equally endangered. Neither would have an advantage. But our universe is not balanced. Matter won. And so the electron thrives while the positron is hunted to extinction within billionths of a second of its creation. Think about what this means. You are born into a universe where every atom, every molecule, every surface, every gas, every liquid, every solid is built from the very particles that will destroy you on contact. You cannot touch anything without being annihilated. The entire physical world is your enemy. Not because it is actively hostile, but because its very composition is incompatible with your survival. This is not a slow process. In most materials, a positron survives for somewhere between 100 picoseconds and a few nanoseconds after entering the material. A picosecond is 1 trillionth of a second. A nanosecond is 1 billionth of a second. That is how quickly matter destroys a positron. The moment it enters any ordinary substance, it begins losing energy through interactions with surrounding atoms. It slows down, and as it slows, the probability of encountering an electron increases. And once an electron gets close enough, the attraction between their opposite charges pulls them together, and annihilation occurs. Let me put those timescales in perspective. A nanosecond, 1 billionth of a second, is to 1 second what 1 second is to about 31.7 years. In the time it takes you to blink, roughly 300 to 400 milliseconds, a positron could have been created and annihilated 300 million times over. These are not timescales that humans can experience or even meaningfully imagine. The reason this happens so quickly is simple. Electrons are everywhere in matter. Consider the air around you right now. Every cubic centimeter of air at sea level contains roughly 2.7 times 10 to the 19th molecules. Each molecule of nitrogen has 14 electrons. Each molecule of oxygen has 16 electrons. The air is saturated with electrons. A positron entering this environment is like dropping a lit match into a room filled with gasoline vapor. Contact is essentially immediate. In solid materials, the electron density is even higher. A positron entering a metal is surrounded by electrons on all sides, at extremely short distances. The annihilation happens almost instantly. Even in the vacuum of space, positrons do not get a free pass forever. Space is not perfectly empty. There are stray atoms, molecules, ions, and free electrons scattered throughout interstellar space. The density is incredibly low, roughly 1 particle per cubic centimeter in some regions of the galaxy. So a positron in deep space would survive much longer than one in Earth's atmosphere. It might travel for thousands or even millions of years before encountering an electron, but eventually, statistically, it will encounter one. And when it does, the result is the same: annihilation. Now, here is something that adds another layer to this story. The positron doesn't just vanish the instant it meets any electron. There is actually a brief, almost poetic intermediate step that sometimes occurs. When a positron slows down enough in a material, it can temporarily capture an electron, and the two particles form a bound state. They orbit each other like a tiny two-body system. This bound state is called positronium, and positronium is one of the strangest atoms in all of physics. It is an atom with no nucleus. Every other atom you have ever heard of has a nucleus at its center made of protons and neutrons, with electrons orbiting around it. Positronium has nothing at the center. It is just an electron and a positron orbiting their common center of mass. It's the simplest bound system you can build from matter and antimatter, and it is entirely temporary. Positronium comes in two forms depending on how the spins of the electron and positron are aligned. If their spins are antiparallel, meaning they point in opposite directions, the system is called parapositronium. If their spins are parallel, meaning they point in the same direction, it is called orthopositronium. Parapositronium has a lifetime of about 125 picoseconds. It annihilates into 2 gamma-ray photons. Orthopositronium lives slightly longer, about 142 nanoseconds, and annihilates into 3 gamma-ray photons. But the key point is the same in both cases. Positronium is not stable. It cannot last. The electron and positron that form it are destined to annihilate each other. The bound state is just the last dance before the end. Positronium was first observed experimentally in 1951 by Martin Deutsch at the Massachusetts Institute of Technology. Its discovery confirmed theoretical predictions about how positrons interact with matter and provided further evidence that the physics of antimatter was well understood. But positronium is more than just a curiosity. It has become one of the most important testing grounds in all of physics. Because positronium is made of only 2 fundamental particles, an electron and a positron, with no nucleus to complicate things, its properties can be calculated from theory with extraordinary precision. The energy levels of positronium the exact frequencies of light it can absorb and emit, the precise rates at which its two forms annihilate. All of these can be predicted using quantum electrodynamics to many decimal places. And then those predictions can be compared to experimental measurements. This makes positronium one of the purest tests of QED that exists. If there were anything wrong with our understanding of how electrons and positrons interact with photons, if there were any flaw in the theory, it would show up as a discrepancy between the predicted and measured properties of positronium. So far, no such discrepancy has been found. The theory and the experiments agree with remarkable precision. Positronium, this fleeting, doomed atom that exists for less than a millionth of a second, has helped confirm that our understanding of quantum electrodynamics is correct to an extraordinary degree. A particle that cannot survive is nonetheless one of our best tools for testing the laws that govern its destruction. Let's take a step back and think about what we have established so far. We know that the positron is a real, physical particle. We know that it was predicted by theory before it was found by experiment. We know that it has the same mass and spin as the electron but opposite charge. We know that it is perfectly stable on its own, and we know that the moment it encounters ordinary matter, which is filled with electrons, it is destroyed through a process called annihilation. This happens incredibly fast, on timescales of trillionths to billionths of a second, because electrons are extraordinarily abundant in any ordinary material. But we haven't yet fully explained what annihilation actually is. We've said the particles are destroyed and that energy is released. But what does that actually mean? What physically happens when a positron meets an electron? Where does the energy come from? Why doesn't the electron just absorb the positron or bounce off it the way particles often bounce off each other? That is what makes this story so compelling. The destruction of a positron by ordinary matter is not like any other process you encounter in daily life. When a rock breaks, the pieces are still there. When wood burns, the atoms are still there, just rearranged into new molecules. When ice melts, the water molecules are still there. In every ordinary physical process, the basic building blocks remain. Annihilation is fundamentally different. In annihilation, the building blocks themselves disappear. The electron and the positron do not break into smaller pieces. They do not rearrange into new particles. They are gone. Their mass, the actual physical substance of which they were made, is converted into energy. This is not a metaphor. The mass literally becomes energy. The particles literally cease to exist. What remains is pure electromagnetic radiation, gamma-ray photons carrying away the energy that was once locked up in the mass of those two particles. This is the most complete destruction possible in physics. There is nothing left to recover. There are no fragments to pick up, no residue to analyze, no trace that a particle was ever there except for the energy it released in the moment of its death. And perhaps the most remarkable thing about all of this is how ordinary it is from the perspective of physics. Annihilation is not exotic. It is not rare. It happens every time a positron meets an electron. Every single time. Without exception. The laws of physics not only allow it, they demand it. We live in a universe that is overwhelmingly made of matter. Every atom in your body, every molecule in the air, every star in the sky is made of matter particles, protons, neutrons, and electrons. Antimatter, the mirror world of positrons and antiprotons and antineutrons, is vanishingly rare. When a positron appears in our world, whether created in a radioactive decay, in a cosmic ray shower high in the atmosphere, or in a particle accelerator in a laboratory, it enters an environment that is fundamentally hostile to its existence. It is surrounded on all sides by the one thing guaranteed to destroy it: electrons. The positron has nowhere to hide. It has nowhere to go. It cannot find a safe corner of our universe because there are no safe corners. Matter is everywhere, and matter contains electrons, and electrons annihilate positrons. The electromagnetic attraction between opposite charges draws the positron toward electrons. The conservation laws of quantum field theory allow the annihilation to proceed, and the mass-energy equivalence discovered by Einstein provides the energy budget for the process. Everything aligns. The positron is doomed from the instant it appears. There is something almost tragic about this if you allow yourself to think of particles in human terms, which of course you shouldn't, but the metaphor is irresistible. The positron is a perfectly good particle. There is nothing wrong with it. It is exactly as valid, exactly as fundamental, exactly as real as the electron. But it was born into the wrong universe. It was born into a universe made of matter, where its opposite number, the electron, is the most common charged particle in existence. In a universe made of antimatter, the positron would thrive. It would be the normal one, and the electron would be the doomed outsider. But our universe is not made of antimatter. It is made of matter. And so the positron's fate is sealed. The question that matters now is what exactly happens in the moment of annihilation. What does it mean for two particles to be erased from existence? Where does the energy come from? And why does this process happen at all? We ended with a question. What actually happens when a positron meets an electron? We know it's called annihilation. We know both particles disappear. We know energy comes out. But what does that physically mean? Because annihilation is not like anything you encounter in everyday life, and understanding it clearly requires us to forget almost everything we think we know about how objects interact. Let's start with what annihilation is not. Because the best way to understand something strange is to first rule out everything familiar. When you throw two tennis balls at each other, they collide. They bounce off. Maybe they deform a little. But after the collision, both tennis balls still exist. They might be damaged. They might have changed direction or shape. But the stuff they are made of is still there. This is an ordinary collision. Two objects meet, interact, exchange energy and momentum, and continue existing afterward. Annihilation is not a collision in this sense. When a positron meets an electron, the particles do not bounce off each other. They are not there anymore after the event. Both particles completely cease to exist. Let's also be clear about what annihilation is not in another sense. It is not absorption. When an atom absorbs a photon, the photon disappears, but its energy is taken up by the atom. The photon is gone, but the atom is still there. But annihilation is not this either. In annihilation, the electron does not absorb the positron. Both particles vanish. There is no surviving particle that absorbed the other. What remains in their place is pure energy in the form of photons, specifically gamma-ray photons. This is a fundamentally different kind of process. In ordinary collisions, objects persist. In absorption, one object persists. In annihilation, nothing persists. The participating particles are entirely, completely, irrecoverably gone. So what exactly happens, step by step? Let's walk through the process carefully. Because the details matter, and they reveal something profound about the nature of matter and energy. The most common form of electron-positron annihilation occurs when both particles are at rest or nearly at rest relative to each other. This is called low-energy annihilation, and it is by far the most typical scenario in ordinary matter. When a positron enters a material, it begins losing energy almost immediately. It interacts with the atoms around it, scattering off nuclei and electrons, losing a little bit of kinetic energy with each interaction. It slows down. Eventually, the positron slows enough that an electron captures it, or the two particles simply drift close enough that their mutual attraction pulls them together. In many cases, the slowing positron and a nearby electron form a short-lived bound state called positronium, where they orbit each other for a fleeting instant. But whether positronium forms or the annihilation happens directly, the end result is the same. The electron and positron come together, and then, in a single quantum event, both particles vanish, and in their place, two gamma-ray photons are created, shooting off in exactly opposite directions. Two photons, not one, not three, two, and they fly apart at 180 degrees from each other, each carrying away exactly the same amount of energy. This is not a random outcome. It is required by the laws of physics, and understanding why requires us to talk about conservation laws. Conservation laws are among the most powerful ideas in all of science. They tell us what can happen and what cannot happen in any physical process. They are not suggestions. They are absolute rules that, as far as we have ever observed, are never violated. And every single one of them is satisfied perfectly by electron-positron annihilation. That is why annihilation is allowed. That is why it happens. Because nothing forbids it. Let's go through the conservation laws one by one. First, conservation of energy. Energy cannot be created or destroyed. The total energy before an event must equal the total energy after the event. Before annihilation, we have an electron and a positron. Each one has mass, and mass is a form of energy. The famous equation E equals mc squared tells us exactly how much energy is locked up in a given amount of mass. Together, they have a combined energy equal to twice the mass energy of a single electron, plus whatever kinetic energy they had from their motion. After annihilation, the two photons carry away exactly the same total energy. Energy is conserved. Second, conservation of momentum. Momentum is the quantity of motion an object has. It depends on mass and velocity, and it has a direction. In the simplest case, the electron and positron are at rest relative to each other. Their total momentum is zero. After annihilation, the total momentum must still be zero. This is why two photons are produced going in opposite directions. Each photon carries momentum, but because they travel in exactly opposite directions, their momenta cancel out. If only one photon were produced, it would carry momentum in one direction, and there would be nothing to balance it. That is why a single photon cannot be produced in electron-positron annihilation when the particles are at rest. You need at least two photons to balance the momentum. Physics demands it. Third, conservation of charge. Before annihilation, we have one electron with a charge of -1 and one positron with a charge of +1. The total charge is 0. After annihilation, we have two photons. Photons have no electrical charge. The total charge is 0. Charge is conserved. Fourth, conservation of lepton number. The electron has a lepton number of +1. The positron has a lepton number of -1. Before annihilation, the total lepton number is 0. After annihilation, the photons carry no lepton number. The total is still 0. Lepton number is conserved. Fifth, conservation of spin angular momentum. Depending on how their spins are aligned, the total spin angular momentum of the system before annihilation can be either 0 or 1. This is accomplished through the specific spin states and polarizations of the two gamma-ray photons. Angular momentum is conserved. Every single conservation law is satisfied. Energy, momentum, charge, lepton number, angular momentum. There is no law of physics that says annihilation cannot happen. On the contrary, every law of physics says it can. And in quantum field theory, if a process is allowed by all conservation laws, it does not merely occur sometimes. It occurs with certainty, given sufficient opportunity. The electron and positron will annihilate, not might, will. It is guaranteed. This is a crucial point that deserves emphasis. In quantum field theory, particles are not little balls bouncing around. They are excitations of underlying quantum fields. The electron is an excitation of the electron field. The positron is an excitation of the same field, but with opposite quantum numbers. The photon is an excitation of the electromagnetic field. Annihilation is the process by which excitations in one field transfer their energy to another field. The electron field settles back down. The electromagnetic field gets excited. That is all annihilation is at the deepest level, a transfer of energy between fields. Let me try to make this idea more vivid because it is genuinely profound, and it changes how you think about what matter actually is. Imagine a calm lake. Now imagine you disturb the surface and create a ripple. That ripple moves across the water. It has energy. It has momentum. It has a location. In many ways, it behaves like a thing, a distinct object moving through the water. But the ripple is not made of different stuff from the lake. It is the lake, temporarily organized into a moving pattern. If the ripple reaches the shore and its energy is absorbed, the ripple disappears. But the water is still there. The energy has been transferred from the ripple pattern to the thermal motion of the water and the shore. Particles in quantum field theory are like ripples on a lake. The electron is not a little ball sitting in empty space. It is a ripple in the electron field, a field that fills all of space. The ripple has energy, momentum, charge, and spin. It behaves like a thing. We detect it as a thing. We call it a particle, but it is really a pattern of excitation in an underlying field. The positron is another ripple in the same field, but with opposite quantum numbers. A ripple spinning the other way, if you like. When an electron and a positron meet and annihilate, what happens is that the ripples in the electron field cancel each other out. Their opposite quantum numbers sum to 0. The electron field becomes calm again at that point. But the energy that was in those ripples doesn't vanish. It has to go somewhere. It transfers into the electromagnetic field, creating new ripples there. Those new ripples are what we call photons. Gamma-ray photons, in this case, carrying away exactly the energy that the electron field ripples had. So annihilation is not the destruction of stuff. It is the quieting of one field and the excitation of another. The total energy in all the fields combined hasn't changed at all. It has just been redistributed. The electron field lost energy. The electromagnetic field gained energy. And from our perspective, watching from the outside, two particles disappeared and two photons appeared in their place. There is one more detail about this picture that is worth understanding, because it explains at the deepest level why the electron and positron can annihilate each other so cleanly. The electron and the positron are not excitations of two different fields. They are excitations of the same field, the electron field. The electron is one type of excitation in this field, and the positron is another type of excitation in the very same field, but with opposite quantum numbers. They are like opposite disturbances in the same medium. Think of a guitar string at rest. If you pluck it upward, you create a vibration. If you pluck it downward, you create another vibration, equal in magnitude, but opposite in direction. Both vibrations are real. Both carry energy. Both are valid disturbances of the string. But if you somehow created both vibrations at the same point on the string at the same time, one going up and one going down, they would cancel each other out. The string would return to rest. The vibrations would be gone. But the energy they carried would not be gone. It would have been transferred into something else, into the sound radiating from the string, into the heat of the string's material, into the motion of the air around it. This is almost exactly what happens in electron-positron annihilation. The electron is the upward vibration of the electron field. The positron is the downward vibration. When they meet, the vibrations cancel. The electron field returns to its ground state at that point. But the energy that was in those vibrations transfers into the electromagnetic field, creating photons. The string goes quiet. The air carries the sound away. This is why the quantum numbers cancel so perfectly. It is not a coincidence that the positron has exactly opposite charge, exactly opposite lepton number, exactly opposite quantum numbers to the electron. It is because they are opposite excitations of the same field. Of course they cancel. They were always two sides of the same coin. Two opposite disturbances in the same underlying reality. Their mutual annihilation is not a strange accident. It is the most natural thing in the world. It is a field returning to rest. This perspective makes annihilation seem less like destruction and more like transformation. The energy doesn't disappear. It changes form. What was mass becomes radiation. What was matter becomes light. The total amount of energy in the universe doesn't change by a single unit. It just shifts from one manifestation to another. But from our macroscopic perspective, the effect is dramatic. Two particles that had mass, that had charge, that occupied space, are suddenly gone, replaced by photons that have no mass, no charge, and that travel away at the speed of light, never to return. The matter has been erased. And in its place, there is only light. Now, let's talk about those photons more specifically. Because the gamma-ray photons produced in electron-positron annihilation have very specific, very precise characteristics. Each gamma-ray photon produced in the annihilation of a stationary electron-positron pair carries an energy of exactly 511 kilo electron volts. This number comes directly from the mass of the electron. The mass of an electron, when converted to energy units using E equals mc squared, corresponds to 511 kilo electron volts. Since the positron has the same mass, the total mass energy of the electron-positron pair is 1.022 mega electron volts. This energy is divided equally between the two photons. This is one of the most precisely predicted and precisely measured quantities in all of physics. When scientists detect gamma rays with an energy of exactly 511 kilo electron volts, They know immediately that they are looking at the signature of electron-positron annihilation. It is a fingerprint, unmistakable and unique. These 511 kilo-electron-volt gamma rays have been detected coming from many sources throughout the universe. They come from the center of our galaxy. They come from solar flares. They come from the regions around black holes and neutron stars. They are one of the primary tools astronomers use to study antimatter in the cosmos. Let me put the energy of these gamma rays in context. Visible light has an energy of roughly 1.8 to 3.1 electron volts per photon. A 511 kilo electron volt gamma ray has about 200,000 times more energy than a photon of visible light. These are extremely energetic photons. They can penetrate through skin, muscle, and bone. They can damage DNA. And they're produced every single time a positron meets an electron. Now I want to address a question that might be forming in your mind. If annihilation is so complete, why doesn't this happen with other particles? Why don't two electrons annihilate each other? The answer goes back to those conservation laws. Two electrons cannot annihilate each other because their combined charge is -2. Photons have no charge. Charge would not be conserved. Physics forbids it. There is also the matter of lepton number. Two electrons have a combined lepton number of +2. Photons have a lepton number of 0. Lepton number would not be conserved. Again, physics forbids it. For annihilation to work, the conservation laws must balance, and they only balance when a particle meets a specific antiparticle. Electron meets positron. Proton meets antiproton. In each of these cases, the quantum numbers are exactly opposite. They cancel. Everything goes to 0. And from 0, you can produce photons, which also carry 0 charge, 0 lepton number, 0 baryon number. Everything balances. This is why the positron, and only the positron, can annihilate with the electron. It is the electron's perfect counterpart, and their meeting produces the cleanest, most complete reaction in all of physics. Let me also address the speed at which this happens. When a positron enters ordinary matter, the process has stages. The positron first undergoes what physicists call thermalization. It enters the material with some amount of kinetic energy. It scatters off atoms and electrons, losing energy with each interaction. The positron slows down. Once the positron has thermalized, it begins to diffuse through the material, wandering randomly. During this diffusion phase, the positron is constantly encountering electrons. And each encounter is a potential annihilation event. The probability accumulates, and the encounters happen incredibly frequently because electrons are so dense in ordinary matter. The net result is that the average positron lifetime in most condensed materials is somewhere between 100 picoseconds and about 500 picoseconds. In a gas at atmospheric pressure, the lifetime might be a few nanoseconds. But regardless of the specific material, the positron's life is measured in fractions of a billionth of a second. It is one of the fastest processes in all of physics that involves the complete transformation of matter into energy. The fact that positron lifetimes are so short and so precisely measurable has led to an entire branch of material science called positron annihilation spectroscopy. Scientists deliberately inject positrons into materials and measure exactly how long they survive before annihilating. The lifetime depends on the local electron density. In a perfect crystal, where atoms are arranged in a regular grid, the positron encounters a predictable density of electrons and has a characteristic lifetime. But if there is a defect in the crystal, a missing atom, a tiny void, a dislocation in the lattice, the positron can become trapped in that defect. Inside the void, there are fewer electrons. The positron lives slightly longer. By measuring the lifetime distribution of many positrons injected into a sample, scientists can detect and characterize defects in the material that would be invisible to other techniques. This is remarkably powerful. Positron annihilation spectroscopy can detect voids as small as a single missing atom in a crystal lattice. It can measure the concentration and size distribution of microscopic pores in polymers, ceramics, and thin films. It is used to study radiation damage in nuclear reactor materials, fatigue in aircraft components, and aging in semiconductor devices. The positron's inevitable, rapid destruction by electrons, the very thing that makes it unable to survive in our universe, is what makes it such an exquisitely sensitive probe of matter's structure. Its death tells us something about the environment in which it died. The exact timing of the annihilation, measured to within a few picoseconds, reveals the architecture of the material at the atomic scale. The technique works because the positron is not just destroyed. It is destroyed in a predictable, measurable way. 2 511 kilo-electron-volt gamma rays, back to back, every time. The timing of those gamma rays, the angle between them, even the slight Doppler shifts in their energy caused by the momentum of the electron, the positron annihilated with all of these carry information. The positron's death is not silent. It is a precisely encoded message about the matter that killed it. There is something deeply instructive about the fact that all conservation laws are perfectly satisfied in annihilation. The universe has rules. Strict, unbreakable rules about what quantities must be preserved. And within those rules, the universe is extraordinarily permissive. If a process does not violate any conservation law, it will happen. And electron-positron annihilation is not just allowed, it is favored. It is energetically favorable, meaning the final state, 2 gamma-ray photons, is a more stable configuration than the initial state. The reaction proceeds spontaneously because the final state is energetically accessible and all conservation laws permit the transition. This is fundamentally different from how we usually think about destruction. When a positron is destroyed by an electron, it is destroyed because the laws of physics actively enable and favor the process. There is no structural failure. There is simply a transition from one allowed state to another, more favorable state. Electron-positron annihilation is like 2 opposite magnets snapping together, but taken to the most extreme possible degree. The electron and positron are attracted by their opposite charges. They come together. And when they do, instead of just snapping together, they undergo a total transformation. All of their mass is converted into energy. It is the ultimate exothermic reaction, the most complete energy release possible. And this brings us to a profound question. We keep saying that the mass is converted into energy. But what does that actually mean? When we say the mass is converted into energy, what we really mean is that the particle itself, the excitation of the quantum field, has ceased to exist, and the energy that was associated with that excitation, the energy that manifested as mass, now manifests as the energy of photons instead. In Einstein's framework, mass and energy are not 2 separate things. They are 2 faces of the same coin. Mass is a form of energy. When the electron and positron annihilate, the energy doesn't change in total amount. It changes in form. What was locked up as the mass of 2 particles is now freely propagating as the energy of 2 photons. The total is exactly the same. Nothing has been lost, nothing has been gained. This is E equals mc squared made real, not as an abstract equation on a blackboard, but as an observable, measurable, physical event. Every time a positron annihilates with an electron, Einstein's equation is being demonstrated. 511 kilo electron volts per particle, 1.022 mega electron volts total, every time, without exception. The theory that describes electron-positron annihilation is called quantum electrodynamics, or QED. It was developed in the late 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. QED predictions agree with experimental measurements to better than 10 decimal places. That is like predicting the distance from New York to Los Angeles to within the width of a human hair. The agreement between theory and experiment in QED is one of the greatest triumphs in the history of science. The single most spectacular example of this agreement involves a quantity called the anomalous magnetic moment of the electron, sometimes referred to as G-2. Every electron behaves like a tiny magnet. The strength of this magnetism can be predicted by QED, but the calculation is extraordinarily complex. It requires accounting for the fact that the electron is constantly surrounded by a cloud of virtual particles, ghostly quantum fluctuations that flicker in and out of existence around it. Among these virtual particles are virtual positrons. They appear for the briefest of instants, interact with the electron, and vanish again. These fleeting appearances of the electron's antimatter counterpart actually change the electron's magnetic properties by a tiny but measurable amount. To calculate G-2 precisely, physicists must account for thousands of these virtual processes, each one involving Feynman diagrams of increasing complexity. The calculation has been pushed to the 10th decimal place. And when experimentalists measure the same quantity in the laboratory, using single electrons trapped in magnetic fields for months at a time, the measured value agrees with the calculated value to better than 1 part in 10 billion. The electron's magnetic moment is known to 12 significant digits on both the theoretical and experimental sides, and the two numbers match. This is the measurement that earns QED its reputation as the most precisely tested theory in the history of science, and the positron is woven directly into this achievement. Without accounting for virtual positrons flickering around the electron, the theoretical prediction would be wrong. The positron's ghostly presence, even when no real positron is anywhere nearby, alters the measurable properties of every electron in the universe. Antimatter is not just something that appears and gets destroyed. It's a part of the quantum fabric that makes ordinary matter behave the way it does. And yet, despite how well we understand the mechanism, there is still something awe-inspiring about it. The fact that two particles can simply cease to exist, that their mass can be entirely converted into light, that this happens spontaneously, inevitably, every time a positron encounters an electron. Annihilation is the universe showing us in the most direct way possible that matter and energy are truly the same thing. The positron enters a world made of electrons, and the electrons, simply by existing, simply by being what they are, guarantee its end. Not through malice, not through intent, but through the cold, beautiful, implacable logic of conservation laws. The charges cancel, the quantum numbers cancel, the mass becomes energy, and the positron is gone. We have now established what annihilation is. Two particles, an electron and a positron, meet and cease to exist. Their combined mass is replaced by 2 gamma-ray photons carrying a total energy of 1.022 mega electron volts. Every conservation law is satisfied. The process is not merely allowed, but energetically favored. It proceeds spontaneously, inevitably, completely. But there is a deeper question lurking behind all of this. Why does annihilation release energy at all? Where does the energy come from? The answer seems obvious at first. The energy comes from the mass of the particles. E equals mc squared. You have heard this equation 1,000 times, but hearing it and understanding it are two completely different things. Most people treat E equals mc squared as a slogan, but the equation is saying something far more radical, far more precise, and far more unsettling than most people realize. An electron-positron annihilation is the purest, cleanest, most direct demonstration of what the equation actually means. So let's take this slowly. The equation has 3 components. E stands for energy, M stands for mass, and C stands for the speed of light in a vacuum, which is approximately 300,000 kilometers per second. The equation says that energy equals mass multiplied by the speed of light squared. That is, energy equals mass times a very, very large number. The speed of light is about 300 million meters per second. When you square that, you get about 9 times 10 to the 16th. That is 90 quadrillion. This is the conversion factor between mass and energy. Every kilogram of mass corresponds to 90 quadrillion joules of energy. To give you a sense of scale, 1 kilogram of matter converted completely into energy would release about 1,400 times more energy than the Hiroshima bomb. And a kilogram is not a lot of mass. It is about the weight of a bag of sugar. There is enough energy locked inside the mass of a bag of sugar to level a major city many times over. This is what E equals mc squared is telling us. Mass is energy, not metaphorically, literally. Now here is the critical thing. In everyday life, we never see this conversion happen completely. When you burn wood, the atoms rearrange themselves into new molecules, releasing the energy stored in their chemical bonds. But the atoms themselves are still there. The products of combustion have very slightly less mass than the reactants. But the mass difference is so unbelievably small, roughly 1 billionth of the total mass, that no scale in existence could measure it. Let me make this even more concrete. A litre of gasoline contains enough chemical energy to drive an average car about 15 kilometers. That energy comes entirely from rearranging chemical bonds. The carbon and hydrogen atoms in the gasoline combine with oxygen atoms from the air, forming carbon dioxide and water, and the energy stored in those original bonds is released as heat, which the engine converts into motion. But if you could somehow convert the entire mass of that same litre of gasoline into energy using E equals mc squared, not just rearranging the bonds but converting the actual atoms into pure radiation, you would get roughly 2 billion times more energy. Enough to drive that same car not 15 kilometers, but around 30 billion kilometers. That is roughly the distance from Earth to Neptune and back, 3 times over, from 1 litre of gasoline. Not because gasoline is special, but because mass itself contains an almost incomprehensible amount of energy. We just never access more than the tiniest fraction of it in chemical reactions. This is the difference between rearranging matter and converting matter. Chemistry rearranges, it moves atoms around, breaks and forms bonds, and skims off the tiny energy differences between configurations. Nuclear physics goes deeper. It rearranges the components inside atomic nuclei, moving protons and neutrons around and skimming off slightly larger energy differences. But annihilation goes all the way. It does not rearrange anything. It converts the matter itself, every last bit of it. And the result is an energy release that dwarfs chemical and nuclear processes by factors of millions or billions. Nuclear reactions are different. In nuclear fission, the products have measurably less mass than the original atom. The mass difference is about 1/10 of 1%. And that tiny fraction of a percent, multiplied by c squared, produces the enormous energies that power nuclear reactors and nuclear weapons. In nuclear fusion, when light atoms combine to form heavier atoms, the same thing happens. That mass difference becomes the energy that powers the stars. But even in nuclear reactions, only a tiny fraction of the total mass is converted into energy. In fission, about 0.1%. In fusion, about 0.7%. The vast majority of the mass remains as mass. Electron-positron annihilation is fundamentally different from all of this. In annihilation, 100% of the mass is converted into energy. Not 0.1%, not 0.7%, 100%, every last bit. The electron and positron are fundamental particles, indivisible, with no internal structure. There is nothing to rearrange, there is only the particle and its mass, and in annihilation, all of that mass becomes energy, completely, without remainder. This is what makes electron-positron annihilation the purest demonstration of E equals mc squared in all of physics. The total conversion of mass into energy with nothing left behind. Let's actually do the calculation. The mass of an electron is 9.109 times 10 to the minus 31 kilograms. The positron has exactly the same mass. So the total mass of the pair is about 1.822 times 10 to the minus 30 kilograms. Multiply this mass by c squared. You get about 1.64 times 10 to the minus 13 joules. In particle physics units, this is 1.022 mega electron volts. Split equally between the two gamma-ray photons, each photon carries 511 kilo electron volts. These numbers have been measured experimentally with extraordinary precision. The measured energy matches the theoretical prediction to many decimal places. The equation works perfectly. 1.64 times 10 to the minus 13 joules might not sound like much, but the energy per unit mass is extraordinary. If you could gather 1 gram of electrons and 1 gram of positrons and let them all annihilate, the total energy released would be about 1.8 times 10 to the 14th joules. That is about the energy of 3 Hiroshima bombs from just 2 grams of material. That is the power of total mass to energy conversion. Compare this to other energy sources. Burning 1 gram of gasoline releases about 47,000 joules. Nuclear fission of 1 gram of uranium releases about 82 billion joules, but annihilating 1 gram of matter with 1 gram of antimatter releases about 180 trillion joules. Annihilation is the most efficient energy release process in the universe because it converts all of the mass. This enormous energy release is not a consequence of some special property of antimatter. Antimatter has the same mass as ordinary matter. The energy comes from the total conversion of mass to energy, and that total conversion is only possible because matter and antimatter are perfect opposites, whose quantum numbers cancel completely. Nothing is left behind to carry charge or lepton number, because all those quantities sum to 0. The slate is wiped clean, and a clean slate means total conversion. This is why two electrons cannot annihilate each other. Their charges don't cancel. Their lepton numbers don't cancel. The conservation laws prevent total conversion. Something must remain to carry the unbalanced quantum numbers, and that something must have mass. Only when a particle meets its exact antiparticle do all quantum numbers cancel. Only then does E equals mc squared operate at full power, with no remainder and no leftover mass. Think of mass as a way of storing energy. An electron stores 511 kilo-electron-volts of energy in the form of its mass. A positron stores the same. Together they hold 1.022 mega-electron-volts. This energy is locked up inside the particle's existence, but annihilation unlocks it. When the quantum numbers cancel, there is no longer any reason for that energy to remain stored as mass. The energy must go somewhere, and it goes into photons. This is happening around us right now. Certain naturally occurring radioactive isotopes undergo beta plus decay, a process that emits a positron from the nucleus. That positron enters the surrounding material, slows down, and annihilates with an electron. Certain atoms in your own body occasionally undergo beta plus decay and emit positrons that are instantly annihilated by nearby electrons. Inside you, right now, E equals mc squared is being demonstrated in miniature. The numbers are tiny, far too small to harm you, but the physics is real. The 511 kilo-electron-volt gamma-ray line has been observed by space-based gamma-ray telescopes, coming from the center of our galaxy, from solar flares, from distant astrophysical sources. Every detection is another confirmation that E equals mc squared is exactly correct. Now let's address something that often causes confusion. People sometimes ask whether annihilation violates the law of conservation of mass. In modern physics, we do not have separate conservation of mass and conservation of energy. We have conservation of mass energy. Mass and energy are the same thing, measured in different units. The total mass energy of the system before annihilation equals the total mass energy after. What has changed is the form. Einstein showed that the true conservation law is conservation of mass energy, and annihilation respects this law perfectly. This shift in understanding from separate conservation of mass and energy to unified conservation of mass energy was one of the most important conceptual revolutions in the history of science. For over 2 centuries, from Newton through the Industrial Revolution, physicists treated mass and energy as entirely separate quantities. Mass was the stuff things were made of. Energy was what made things move or heat up. They seemed to have nothing to do with each other. A kilogram of iron was a kilogram of iron whether it was hot or cold, moving or still. Its mass didn't change when you heated it or dropped it. Or so everyone thought. Einstein showed that this was wrong. When you heat a kilogram of iron, you are adding energy to it, and that energy has mass. A hot kilogram of iron is very, very slightly heavier than a cold kilogram of iron. The difference is unbelievably tiny, far too small to measure with any scale, but it is real. It is a consequence of mass-energy equivalence. Energy has mass, mass has energy. They are the same thing expressed in different units, connected by the conversion factor c squared. For everyday purposes, the old separate laws work perfectly well, because the mass equivalent of everyday energies is too small to detect. But at the subatomic level, in nuclear reactions, and especially in particle-antiparticle annihilation, the interconversion becomes dramatic and impossible to ignore. Annihilation is the process that forces us to abandon the old framework entirely. You simply cannot describe annihilation using separate conservation of mass and energy. Mass disappears, energy appears. The only way to make the books balance is to recognize that they were never separate books to begin with. They were always one ledger, one conserved quantity. Mass energy. Let me now explain why annihilation is specifically energetically favored. Consider an electron and a positron at rest near each other. They have a combined mass energy of 1.022 mega electron volts. Now consider the final state. Two gamma-ray photons flying apart in opposite directions. The total energy is the same, but there is no energy barrier preventing the annihilation. There is no threshold that must be overcome. The electron and positron attract each other. They simply come together and convert. The process is effortless. Contrast this with the reverse process. Can two gamma-ray photons spontaneously produce an electron-positron pair? Yes, but it is much harder. This is called pair production, and it requires the photons to have at least 1.022 mega electron volts of combined energy. Annihilation has no such threshold. A positron and electron at rest already have more than enough mass energy. The asymmetry is striking. Annihilation is easy. Pair production is hard. Let me explain why pair production from two colliding photons is so extraordinarily rare, because it illuminates something important about how the universe works. Two photons traveling through space almost never interact with each other. Light passes through light. You can shine two flashlight beams through each other, and they pass right through without any effect on either beam. This is because photons do not carry electric charge, so they do not feel the electromagnetic force directly from each other. They can interact, but only through extremely rare quantum mechanical processes involving virtual particle loops, processes so unlikely that for all practical purposes, light is transparent to light. For two photons to produce an electron-positron pair, they must not only have enough combined energy, at least 1.022 mega electron volts, but they must also collide in exactly the right way. The probability of this happening is extraordinarily small. In most environments, it essentially never occurs. This is why the more common form of pair production requires a third party, a nearby atomic nucleus, to participate. When a single high-energy gamma-ray photon passes close to the intense electromagnetic field of a heavy nucleus, that field provides the necessary conditions for the photon to split into an electron-positron pair. The nucleus itself barely moves. It absorbs a tiny amount of recoil momentum, which is necessary to satisfy conservation of momentum. Without this recoil partner, a single photon in empty space could never produce a pair, because a single photon traveling in one direction carries momentum that cannot be balanced by two particles created at rest. The nucleus solves this problem by absorbing the leftover momentum. It is like a wall that absorbs the kick of a gun. The heavier the nucleus, the more easily it absorbs the recoil, which is why pair production is more common near heavy elements like Li than near light elements like hydrogen. This means pair production preferentially happens in dense, high-energy environments, near the cores of massive stars, in the jets of active galactic nuclei, in the showers of secondary particles created when cosmic rays hit Earth's atmosphere. And in every one of these cases, the positron created by pair production finds itself immediately immersed in ordinary matter. It has been born inside the very environment that guarantees its destruction. This asymmetry between creation and destruction is at the heart of why positrons do not survive. Creating a positron requires a significant investment of energy and specific conditions. Destroying a positron requires only the presence of an electron, which is the most common charged particle in the universe. Creation is difficult and rare. Destruction is easy and ubiquitous, but of all the processes in the universe that demonstrate mass-energy equivalence, electron-positron annihilation is the cleanest. 100% conversion. No waste, no leftovers. It is the purest expression of Einstein's insight that mass is energy, and energy is mass. And this purity is exactly what makes the positron's fate so dramatic. The positron does not slowly lose mass over time. It exists fully with all of its mass until the instant it encounters an electron, and then in a single quantum event, 100% of its mass is converted into energy, all at once, complete, total, irreversible. The positron does not fade away. It is erased. Erased because E equals mc squared is not just an abstract relationship. It's a physical law that operates on real particles in real time. One more thing worth saying. If you could scale up the process, 1 kilogram of antimatter annihilating with 1 kilogram of matter would release about 1.8 times 10 to the 17th joules. That is roughly the energy of 43 million tons of TNT, the most powerful nuclear weapon ever detonated. The Tsar Bomba released about 2.1 times 10 to the 17th joules. So 2 kilograms total would release nearly the same energy as the largest nuclear weapon ever built. We do not have the technology to produce antimatter in such quantities. The total amount of antimatter ever produced by humanity is measured in nanograms. And storing it is an even greater challenge, because antimatter annihilates on contact with any container made of ordinary matter. But the physics is clear. The energy is real, and every single time a positron meets an electron, that energy is demonstrated. Immeasurable, detectable gamma-ray photons carrying exactly the energy that ER equals mc squared predicts. The positron's destruction is not just an event, it is a proof. A proof that mass is energy. A proof that the universe at its deepest level is made of something that can transform from solid matter into pure light and back again, governed by laws of breathtaking precision and inescapable consequence. So far we have explored what a positron is, what happens when it meets an electron, and why that process releases energy. We now know that annihilation is the complete conversion of mass into electromagnetic radiation. That is demanded by conservation laws, and that it is the purest demonstration of E equals mc squared in all of physics. But all of this raises a much larger question. A question that takes us from subatomic particles to the structure of the entire cosmos. If positrons are perfectly valid particles, if they are just as fundamental and just as stable as electrons, then where are they? If annihilation works both ways, if high-energy photons can produce electron-positron pairs just as electron-positron pairs can produce photons, then why isn't the universe filled with equal amounts of matter and antimatter? Why do we live in a universe overwhelmingly made of matter, where positrons are destroyed almost the instant they appear? This is one of the deepest and most important unsolved problems in all of physics. And to appreciate it fully, we need to start with where positrons actually come from in the universe we observe today. Positrons are not merely theoretical, they are produced naturally, all around us, all the time. One of the most common sources is a type of radioactive decay called beta plus decay. In beta plus decay, a proton inside an unstable atomic nucleus transforms into a neutron, releasing a positron and a neutrino in the process. Potassium-40, which is present in bananas, in soil, in your own muscles and bones, occasionally undergoes beta plus decay. When it does, a positron is emitted from the nucleus. That positron enters the surrounding material, and within picoseconds to nanoseconds, it encounters an electron and annihilates. 2 511 kilo electron volt gamma rays are produced. This is happening inside your body right now in tiny, harmless quantities. Your own atoms are producing antimatter, and your own atoms are immediately destroying it. Another natural source of positrons is cosmic rays. High-energy particles from deep space constantly bombard Earth's atmosphere. When these cosmic rays collide with atoms in the upper atmosphere, they produce showers of secondary particles, including positrons. The positrons produced in these showers do not last long. They slow down in the atmosphere and annihilate with atmospheric electrons within fractions of a second. Positrons are also produced in some of the most extreme environments in the universe. Near neutron stars, the intense magnetic fields can produce electron-positron pairs from the vacuum itself. Near black holes, the superheated gas reaches temperatures so high that photon-photon collisions routinely produce matter-antimatter pairs. The European Space Agency's Integral satellite, launched in 2002, has detected a strong glow of 511 kilo electron volt gamma rays coming from the region around the galactic center. This tells astronomers that vast numbers of positrons are being produced somewhere in the inner galaxy and annihilating with electrons in the interstellar gas. The exact source is still debated. Some likely come from radioactive isotopes produced in supernova explosions. Some may come from interactions involving the supermassive black hole at the galactic center, Sagittarius A star. But the 511 kilo electron volt signal is unmistakable. It is the calling card of electron-positron annihilation, observed on a galactic scale. In every one of these cases, the story is the same. Positrons are created through various high-energy processes. They enter a matter-dominated environment. They encounter electrons almost immediately, and they annihilate. Creation is temporary. Destruction is permanent. This brings us to one of the most remarkable practical applications of positron annihilation, one that saves lives every day. It is called positron emission tomography, or PET scanning. In a PET scan, a patient is injected with a small amount of a radioactive tracer. The most commonly used tracer is a modified glucose molecule called fluorine-18 FDG. The fluorine-18 isotope is unstable. It undergoes beta plus decay, emitting a positron from its nucleus. Because the tracer is chemically similar to glucose, it is absorbed by cells that use glucose for energy. Cancer cells, which typically have high metabolic rates, absorb more of the tracer than normal cells. Once inside the body, the fluorine-18 atoms begin decaying. Each decay emits a positron. That positron travels less than a millimeter before encountering an electron. Annihilation occurs. 2 511 kilo electron volt gamma rays are produced, flying off in exactly opposite directions. The PET scanner is a ring of gamma ray detectors that surrounds the patient. When two detectors on opposite sides register gamma rays at almost exactly the same time, the system knows that an annihilation event occurred somewhere along the line connecting those two detectors. By recording millions of these simultaneous events, the scanner builds a three-dimensional image showing where the annihilation events are concentrated. The mathematics behind this reconstruction is elegant. Each pair of simultaneously detected gamma rays defines a straight line through the patient's body. The annihilation event happened somewhere along that line, but the detectors alone cannot tell you exactly where along the line it occurred. However, when you record millions of these lines, all crossing through the body at different angles, a pattern emerges. The lines cluster and intersect most densely in the regions where the most tracer has accumulated. By using mathematical algorithms similar to those used in CT scanning, the computer reconstructs a three-dimensional map of tracer concentration throughout the body. Regions with high tracer uptake, which produce more positrons and therefore more annihilation events, appear as bright spots on the image. The spatial resolution of a modern PET scanner is about 4 to 5 millimeters, which means it can detect abnormalities smaller than a pencil eraser. This is possible because of the precision of the physics involved. The two gamma rays are produced at exactly 180 degrees apart. They each carry exactly 511 kilo electron volts. These precise, predictable properties are what make the coincidence detection work. If annihilation produced photons at random angles or with random energies, the technique would be impossible. It works because the physics of annihilation is exact. Every event follows the same rules. Every pair of gamma rays carries the same energy and flies apart in the same geometry. The predictability of the positron's death is what makes it medically useful. This is how doctors find tumors, assess brain function, evaluate heart disease, and monitor cancer treatments. The entire technology depends on the fact that positrons are instantly annihilated by ordinary matter, and that the annihilation produces two gamma rays with a specific, predictable energy flying in opposite directions. It is one of the most elegant connections between fundamental physics and practical medicine that has ever been achieved. But PET scanning does not answer the deepest question. It does not explain why matter dominates over antimatter. To address that question, we need to go back to the very beginning. The Big Bang. Current cosmological models tell us that in the first fractions of a second after the Big Bang, the universe was unimaginably hot and dense. Temperatures were so extreme that photons had enough energy to spontaneously produce particle-antiparticle pairs. Electrons and positrons were created and annihilated in roughly equal numbers. The universe was a seething soup of matter and antimatter in almost perfect balance. As the universe expanded and cooled, the temperature dropped. The photons lost energy. Eventually, the average photon no longer had enough energy to produce new pairs. The creation stopped, but the annihilation continued. Every time an electron met a positron, they annihilated. This should have continued until all the matter and all the antimatter were gone, leaving a universe filled with nothing but photons. But that is not what happened. And the reason it is not what happened is one of the greatest mysteries in modern physics. Something caused a tiny imbalance between matter and antimatter in the early universe. For every billion antimatter particles, there were roughly 1,000,000,001 matter particles, a surplus of about 1 part in a billion. When the annihilation was complete, the billion pairs on each side were gone, converted into the photons. But that one extra matter particle in every billion had no antimatter partner. It survived. And those leftover particles became everything. Every proton, every neutron, every electron in the universe today is part of that 1 in a billion surplus. Every star, every planet, every galaxy, every living thing is the residue left over after the great annihilation. You are made of the leftovers. The photons produced by all that annihilation are still here too, stretched by the expansion of the universe from gamma rays to microwaves over billions of years. We detect them today as the cosmic microwave background radiation. The cosmic microwave background is one of the most extraordinary observations in all of science. It fills the entire sky. It comes from every direction with almost perfectly uniform intensity. Its temperature today is about 2.725 degrees above absolute zero, which corresponds to microwave radiation with a peak wavelength of about 1.1 millimeter. But this faint, cold glow was not always faint or cold. In the earliest moments after the Big Bang, when the Great Annihilation was underway, the photons produced were gamma rays, incredibly energetic and intensely hot. The universe at that time was a blinding inferno of radiation, far hotter than the core of any star that exists today. But as the universe expanded, space itself stretched. And as space stretched, it stretched the wavelengths of those photons along with it. Gamma rays became X-rays, X-rays became ultraviolet light, ultraviolet became visible light became infrared. And finally, after 13.8 billion years of expansion, those photons have been stretched all the way into the microwave part of the spectrum. They are still here. They are still everywhere. But they have been cooled and diluted by the expansion of the universe from a raging inferno into a faint whisper. When you tune a television to a channel with no signal, a small fraction of the static you see on the screen is caused by cosmic microwave background photons hitting the antenna. You are literally seeing ancient photons whose abundance was shaped by the epoch when matter and antimatter annihilated each other in the earliest moments of the universe. The annihilation that shaped everything is not just a historical event. Its evidence is all around us, filling every cubic centimeter of space with roughly 400 photons left over from that ancient destruction. It tells us that there are roughly 1.6 billion photons for every particle of matter in the universe today. That ratio is a direct consequence of the annihilation that occurred in the early universe. Think about what that ratio means for a moment. For every single atom in your body, there are roughly 1.6 billion photons in the cosmic microwave background. For every proton in every star in the sky, 1.6 billion photons. The universe is overwhelmingly made of light, not matter. Matter, the stuff of stars and planets and people, is the rounding error. It is the tiny residue left behind after almost everything annihilated. If you could somehow gather up all the matter in the observable universe, every galaxy, every star, every planet, every grain of dust, and place it alongside all the cosmic microwave background photons, the photons would outnumber the matter particles by more than 1 billion to 1. You are not made of the main ingredient of the universe. You are made of the leftover trace. The universe is a sea of ancient light with scattered islands of matter floating in it. And those islands, those tiny impurities in an ocean of radiation, are everything you have ever seen, touched, or known. Every structure in the cosmos, from the largest galaxy cluster to the smallest bacterium, exists only because of a 1 in a billion imbalance that saved a trace of matter from the Great Annihilation. The rest, the overwhelming majority of what the Big Bang produced, is the cosmic microwave background. Ancient photons from ancient annihilations, still filling every cubic centimeter of space, still carrying the memory of the epoch when matter and antimatter destroyed each other almost completely. But why was there an imbalance at all? If the laws of physics treat matter and antimatter symmetrically, then the Big Bang should have produced exactly equal amounts of both. And the subsequent annihilation should have been perfectly complete. No matter, no antimatter, no us. The fact that we exist means that the laws of physics are not perfectly symmetric between matter and antimatter. Finding that asymmetry is one of the biggest quests in modern particle physics. In 1967, a Russian physicist named Andrei Sakharov laid out 3 conditions that must be satisfied for a matter-antimatter asymmetry to develop. First, there must exist processes that violate the conservation of bare eon number. Second, there must be a violation of CP symmetry, the combination of charge conjugation and spatial reflection. Third, the universe must go through a period where it is not in thermal equilibrium. We know that CP symmetry is violated in nature. This was first demonstrated experimentally in 1964 by James Cronin and Val Fitch, who observed that certain particles called kaons decay slightly differently from their antiparticles. But the amount of CP violation observed is far too small to explain the observed asymmetry. Something else must be contributing. There must be additional sources of CP violation that we have not yet discovered, or entirely new physics beyond what we currently understand. Let me explain the Sakharov conditions a bit more carefully, because they are the roadmap for solving perhaps the biggest mystery in cosmology. The first condition, violation of bare eon number, is necessary because bare eon number essentially counts how much matter there is versus how much antimatter. If bare eon number were always perfectly conserved, then every reaction that created a proton would also have to create an antiproton, and every reaction that destroyed an antiproton would also have to destroy a proton. The count would stay balanced forever. You could never end up with more matter than antimatter. Something must occasionally allow the creation of matter particles without a corresponding antiparticle, or the preferential destruction of antiparticles over particles. The second condition, CP violation, is perhaps the most subtle. Imagine watching a physical process and then watching the same process in a mirror, but with every particle replaced by its antiparticle. If CP symmetry were perfect, the mirrored version would be identical to the original. Matter and antimatter would behave in exactly the same way, under exactly the same circumstances. No experiment could ever distinguish them. And if no experiment can distinguish them, no process can favor one over the other. Any reaction that produced slightly more matter would be exactly balanced by the mirrored reaction that produced slightly more antimatter. The net result would be zero asymmetry. For an imbalance to develop, CP symmetry must be broken. Matter and antimatter must not behave identically. There must be some measurable difference in how they interact with the forces of nature. The third condition, departure from thermal equilibrium, is like the requirement that you take a step before you can move forward. In thermal equilibrium, every process runs at the same rate as its reverse. Particles are created as fast as they are destroyed. Any asymmetry that develops is immediately washed out by the reverse reaction, restoring the balance. Think of it like trying to fill a bathtub when the drain is open at exactly the same rate as the faucet. The water level never changes. The universe must pass through a phase where this balance is disrupted, where the drain and the faucet are running at different rates, so that the asymmetry produced by the first two conditions can be locked in and preserved. All three conditions are necessary. Missing any one of them makes the asymmetry impossible. And while we have evidence that all three are at least partially met in nature, the known physics falls far short of explaining the observed asymmetry by many orders of magnitude. This is where the frontier of physics stands today. Experiments at the Large Hadron Collider at CERN are searching for new sources of CP violation. Experiments studying neutrinos are investigating whether these ghostly particles might hold the key. At CERN, the LHCb experiment specifically studies particles called B mesons, which contain a bottom quark. These particles and their antiparticles have been shown to decay at slightly different rates, confirming that CP violation exists beyond the kaon system where it was first discovered. But even combining all known sources of CP violation from quarks, the total effect is millions of times too small to explain the observed matter-antimatter asymmetry. The universe's books don't balance with the physics we know. Something else must be out there. Neutrinos are a particularly promising avenue of research. These ghostly particles, which barely interact with ordinary matter, come in three types and can oscillate between those types as they travel. If neutrinos and antineutrinos oscillate differently, that would be a new source of CP violation in the lepton sector, rather than the quark sector. Several experiments around the world are racing to measure this. The results could reshape our understanding of why matter survived the early annihilation. There are even more exotic possibilities. Some theories propose that the matter-antimatter asymmetry was generated not by known particles at all, but by hypothetical super-heavy particles that existed only in the extreme temperatures of the very early universe. Particles that decayed preferentially into matter over antimatter before they themselves vanished. These models, called leptogenesis and baryogenesis scenarios, are mathematically elegant but remain unproven. Testing them may require particle accelerators far more powerful than anything that exists today, or it may require insights from cosmological observations that we have not yet made. While the theoretical search continues, experimentalists are doing something remarkable. They are building actual atoms of antimatter and studying them directly. At CERN, the Alpha experiment has succeeded in creating and trapping antihydrogen, the antimatter counterpart of the simplest atom in the universe. An antihydrogen atom consists of an antiproton at its center with a positron orbiting around it, held together by the same electromagnetic force that holds ordinary hydrogen together. It is the antimatter atom we described earlier when we imagined an antimatter universe, and now it exists in a laboratory. Creating antihydrogen is extraordinarily difficult. Antiprotons must be produced in high-energy collisions, slowed down, and cooled to extremely low temperatures. Positrons must be collected and similarly cooled. Then the two must be carefully combined under conditions that allow them to bind into atoms rather than simply annihilating on contact with the walls of the apparatus. The entire process takes place inside a magnetic bottle, a precisely shaped magnetic field that holds the neutral antihydrogen atoms in place without letting them touch any material surface. Because the moment an antihydrogen atom touches any ordinary matter, the positron finds an electron, the antiproton finds a proton, and the atom annihilates instantly. The Alpha team has held antihydrogen atoms in their magnetic trap for many hours at a time. During that time, they can study the atom's properties. They have measured the spectrum of antihydrogen, the specific frequencies of light it absorbs and emits, and compared it to ordinary hydrogen. So far, the spectra are identical to the precision of the measurements. This is exactly what CPT symmetry predicts. But physicists keep pushing the precision higher, because even the tiniest difference between hydrogen and anti-hydrogen would be a revolutionary discovery. It would mean that CPT symmetry is broken, which would require fundamentally new physics. Even more recently, the AlphaG experiment at CERN has measured how anti-hydrogen behaves in Earth's gravitational field. The question sounds almost absurd. Does antimatter fall up or down? Every theory we have says it should fall down, just like ordinary matter. But until you actually test it, you don't know for certain. The results confirm that anti-hydrogen falls downward under gravity, just as normal hydrogen does. Antimatter is attracted by gravity, not repelled. The antimatter universe we described earlier, with its anti-stars and anti-planets, would indeed be held together by the same gravity that holds ours together. These experiments are more than curiosities. They are probing the deeper symmetries of nature with real antimatter atoms, testing whether the laws of physics truly treat matter and antimatter as mirror images. So far, the mirror holds, but the search for even the smallest crack in that mirror continues, because finding one could explain why we exist at all. But for now, the origin of the matter-antimatter asymmetry remains a mystery. And this brings us full circle to the positron. The positron is a perfectly good particle, it is stable, it obeys all the same laws of physics as the electron. But it was born on the losing side of a cosmic lottery. At some point in the first fraction of a second after the Big Bang, a process we do not yet understand tipped the scales in favor of matter. And that tiny tilt meant that after the Great Annihilation, matter survived. Antimatter did not. Today, the positron exists only as a fugitive in a hostile world. It is created in radioactive decays, in cosmic ray showers, in extreme astrophysical environments. And every time, it is almost immediately destroyed by the matter that fills our universe. It cannot exist for more than a few billionths of a second in any ordinary material before the overwhelming abundance of electrons erases it. And yet, the positron is not a failure. It is a window. Through the positron, we see E equals mc squared in action. We see conservation laws dictating fundamental processes. We see the fingerprints of the early universe, the echo of a time when matter and antimatter existed in almost perfect balance. And we see the profound mystery of why that balance was broken. A mystery that, if solved, would explain nothing less than why the physical universe exists at all. Every PET scan that detects a tumor is a testament to the positron's brief existence and predictable death. Every 511 kilo electron volt gamma ray detected from the galactic center is a message from positrons dying far away. Every measurement of the cosmic microwave background is a record of the ancient annihilation that shaped the universe. Let me leave you with this thought. You are made of matter. Every atom in your body is ordinary matter, and that ordinary matter exists because of a 1 in a billion asymmetry in the early universe that no one fully understands. If the balance had been perfect, the annihilation would have been total. Nothing would remain except a universe of cooling photons. No atoms, no molecules, no stars, no planets, no life, no you. You exist because the universe is slightly imperfect. You exist because something broke the symmetry between matter and antimatter by the smallest possible margin. And that smallest possible margin was enough. The positron is your mirror twins particle. It is the ghost of the antimatter that almost won. Every time a positron appears in our universe and is promptly annihilated, it is a reminder of what almost was. A universe of nothing, a universe of pure light. But instead, something tipped the balance, something saved matter. And the result is everything you see, everything you touch, everything you are. The positron cannot survive in our universe. That is not a defect of the positron. It is a feature of the universe, and the physics that destroys the positron, the annihilation, the gamma rays, the precise energy predicted by E equals mc squared, that same physics is what confirms how the universe works at its most fundamental level. Every positron that has ever existed in our matter-dominated cosmos has faced the same fate. Created in a flash of energy, surrounded immediately by the electrons that saturate every corner of the material world, drawn to those electrons by the electromagnetic attraction between opposite charges, and then in a quantum event lasting less than a trillionth of a second, both particles vanish. Their mass becomes light, their existence becomes energy, and the universe continues as if the particle had never been there at all. This is the story of the positron, a particle with every right to exist, a particle identical to the electron in every way except the sign of its charge, a particle that, in a universe of antimatter, would be the normal one. But in our universe, the universe of matter, the positron is an outsider, a spark that appears and is instantly extinguished by the overwhelming presence of its opposite. The next time you hear about antimatter, remember what you have learned tonight. Remember that annihilation is not science fiction. It is happening right now, inside your body, in the atmosphere above you, at the center of the galaxy. Remember that it is the purest conversion of mass into energy that physics allows. And remember that the deepest question of all, why matter won and antimatter lost, remains unanswered. It is one of the great open mysteries of our time, connecting the smallest particles to the largest structures, the physics of annihilation to the existence of everything. We are the margin. We are the residue. We are the one extra particle in every billion that survived the great annihilation. And the positron, erased by the matter world the instant it appears, is the echo of everything we almost weren't. Thank you for joining me on this journey into the heart of matter and antimatter. If you found this exploration valuable, a like or subscribe would mean a lot. And the next time you look at anything, a wall, a glass of water, your own hand, remember that the atoms you are seeing are the survivors. They are the matter that outlasted the annihilation. And inside those atoms, electrons orbit their nuclei, each one carrying the charge that makes positrons impossible visitors in our world. Every positron that briefly flickers into existence and is instantly erased is proof of the extraordinary physics that makes our universe what it is. Sleep well tonight, knowing you are made of the matter that won. Good night.